Hello everyone, and warm welcome to our today's webinar. My name is Marek, and I'm a sales manager in Nenovision. And today we would like to deep dive together with you into the fascinating world of a chip and show you how the semiconductor failure analysis could be elevated onto the next level with an AFM inside of an SEM. But before we start, I wanted to do a quick introduction to our company, Nenovision. So you have an idea who we are. We are a company based in Czech Republic in a city called Brno. And although that from the global perspective, Brno is quite a small city, you might have already know about it. And why is that? It's because 1/3 of the whole SEM global production comes from Brno. So being able to stand side by side with the big companies such as Thermo Fisher Scientific, Tescan, or DeLong Instruments, and to carry more than 70 years of experience in advanced optics and microscopy, it is simply a great place for us to be and to make sure that we manufacture a state-of-the-art system that is keeping up the pace with the current industrial and scientific needs. This year, it actually marks our 10th anniversary, and with the global network of customers and partners, we are proud to have a front row seat in the relentless race of a semiconductor research and development. But let me come back a bit closer to the topic of today. And to do that, I wanted to mention a few of these questions. Do they sound familiar to you? If they do, then I believe that our webinar will be tailor-suited exactly to your needs. And if they don't, well, you don't need to run away. There will be plenty of information for anyone interested in semiconductor research and analysis. So please stay with us. Additionally, if you have any questions during the webinar, do not hesitate to put them into the Q&A section of this call, and we will be happy to answer these during or after the webinar. And without further ado, let me please welcome here my colleague Veronika Hegrova, who is the head of our application team and who will guide you through the exciting world of a semiconductor chip and its failure analysis. Veronika, the stage is yours.
Thank you, Marek, for the introduction. And thank you, everyone, for joining our webinar. So without further delay, let's jump into the semiconductor failure analysis and how we do it with the AFM-in-SEM technology. So in today's webinar, I'd like to start with the introduction of the AFM-in-SEM technology, what it is, where it can be used. Then I will introduce some of the challenges and needs in the semiconductor FA. Further, we will go through the site-specific in-situ failure analysis workflows we're doing, and we will show it on the application examples. So you see where to use it. At the end, there's going to be a summary and Q&A section where we will answer some of the questions that you might have during this webinar. So let's start with the introduction. Most of you probably know what AFM and SEM is. So just quickly, both of these technologies are used in nanoscale analysis. And both of them, as they are using similar scales, being able to merge them together can give us more. But how they are used, so these complementary techniques, AFM is using a physical probe and measures the interactions between the physical probe and the sample surface, whereas the SEM utilizes the interactions between the sample and the focused beam of electrons or ions. So when we merge them together, what we see over here is the AFM LiteScope head sitting on the SEM stage, and behind it now is the chamber open, is the SEM. And so how it can be useful for the site-specific failure analysis. So as these techniques use different principles of operation, then we can combine different information from 3D, high-resolution 3D topography, for instance, electrical properties, combined together with fast 2D imaging with wide, very diverse view field ranges, and modify the surface, for instance. For the semiconductor analysis, I would point out topography, conductivity maps, or dopant concentration from the AFM branch, and SE, BSE, EBAC from the SEM part. And also we can correlate the image, or we can navigate easily. You can see very sharp tip over here. Thanks to the SEM, we are able to precisely navigate to the region of interest. We are also compatible with several different, for instance, SEM stops for the TM lamella preparation. We have different scanner sizes. AFM probe movement is allowed by the macromotors XYZ, and the whole stage is moving as you are used to with the SEM, very precisely. How it looks like in the real life. So we can see the AFM at this moment tilted, SEM column very close to the sample, and plasma FIB or FIB column. So with this setup, we can measure in situ. We can prepare the sample surface and analyze it directly. We have, as you can see, the probe was at the bottom, so we have a protection of the probe so it doesn't get dirty when FIB milling. And this is all happening in one vacuum cycle. Let's go outside of the SEM chamber, how the setup for the AFM-in-SEM looks like. So the two cables from the LiteScope head are going via flange to our control unit nanobox, which is connected to SEM PC and SEM detectors. And the software is running within the control unit, so no installation is needed, and everything is then operated from the SEM PC, both the AFM UI and SEM UI. A LiteScope has a lot of diverse modes of operation. In today's webinar, we will cover electrical properties such as conductivity mapping, local electrical properties, dopant concentration mapping, and in the spectroscopy mode, we will see the current voltage characteristics. Optional accessories which are compatible and very useful for this solution is a sample rotation, which allows larger samples or more samples to be analyzed at once, and especially we can precisely rotate to the exact position for FIB milling. For very sensitive samples, sample transfer module is an effective solution to safely transfer the sample without touching the air or humidity. And as it has automatic loading shuttle, it's quite easy to put the sample in and out. So at this moment we have we know the hardware, and let's have a look at some of the challenges and needs in the semiconductor failure analysis. As you know, the semiconductor devices are shrinking. So there are similar challenges across different fields like packaging, optoelectronics, logic, memory devices, or power devices. And in order to create such a devices and analyze them and find the failures, complex and multi-instrumental analysis is required to tackle these issues at nanoscale. IMEC created quite a nice potential roadmap extension, which I liked very much. So as you can see, from 2018, there was a 7 nanometer technology, Nowadays, we're getting smaller and we're around 2 nanometer technology. And it's expected to go even to smaller devices. But there is, of course, some limit. So in order to get to smaller devices, as well, the architecture has to change of the semiconductor structures. So from FinFET to gate-all-around, and not only the architecture, but as well the technologies which fabricate them and find the failures. So as Edfas in the magazine said, that there are several key technologies in the next-gen tools, and they described that SEM, focus ion beam, AFM are included in the next-gen tools for such structures. How does the standard procedure look like? So definitely you're familiar from yield trend to production test, making the diagnostics, doing the failure analysis, find out what needs to be fixed and redesigned. And we are going in this cycle until the device is correct and can continue further. And so where does the LiteScope fit in? Here in the failure analysis. And let's get a little closer to the advanced failure analysis. As you know, the structures are very complex and will be even more complex in the future. And so being able to find a very localized failure that is happening, for instance, within one node, and identify it and then characterize it, this is actually the most important thing to analyze. So from the current challenges, being very site-specific is important. And as the nodes are shrinking, we have to have better and better instrumentation. Surface oxidation plays quite a role for the especially conductivity mapping or IV spectroscopy to have a good data analyzed, not covered with some oxide. And last but not least, analyzing the invisible defects, because many times the finished analysis is with no defect found, as it was simply not detectable with the traditional optical or SEM imaging. So these are some of the challenges that are currently and will be in the future as we are going smaller. And our solution is tackling these issues with our site-specific in-situ failure analysis with AFM-in-SEM. But this solution would not be possible without our cooperation with experts. So big thanks goes to our Umberto Celano from Arizona State University for his insight, his ideas, where we could go and finding out what's possible here. I'd like to thank to Thermo Fisher Scientific as well for great help with the sample preparation. Michael Lorenz from onsemi for giving us ideas and challenges, what they are working on and what they would need from the scanning spreading resistance microscopy. And last but not least, our in-house semicon expert, Rosalinda Ring, for a big help and heads up what we should develop. So our solution workflow for the failure analysis is from the FIB milling. We can tilt back and forth as we wish. Then the probe is going from the docking position to above the sample surface, navigating and approaching to the sample surface. Then we scan the sample. We can observe it simultaneously with SEM, and then we exit with the probe. This we can repeat over and over again. So this solution gives us several benefits. site-specific electrical characterization is first of them I would mention that we can precisely navigate directly to a specific via or a transistor. And as we are merging the sample preparation and the analysis, we avoid the surface oxidation or contamination because it just have never got away from the chamber. So we are doing the whole procedure within the same vacuum cycle, which also reduces the time and cost per the analysis, as we're not transferring the sample and we eliminate redundant tool usage. So what you've just seen was the AFM directly integrated in plasma FIB-SEM environment, which allows us in-situ workflow from when the failure was localized, so we can prepare the sample to this failure. Then we navigate the tip, analyze in-situ AFM, which means dopant mapping, conductivity, topographical characterization. Then we correlate it together with SEM-based techniques, and we can compare it and understand the failure. So the failure at the end is analyzed. So there are some cycles. As for the delayering process, I will be talking about it later, or the calibration, and all of it was without compromising the sample integrity. So this, you just seen the workflow procedure, and we will have a look at the application examples.
Veronica, maybe before we go to the actual use cases, let me just jump in for a bit. I just want to quickly remind you about the Q&A section of this event, and that it's already open, and we would be more than happy to receive any questions you might have regarding our LiteScope or regarding its semiconductor application. You can place your questions directly into the Q&A part of this webinar window. It should be right on the top bar, right next to the chat function. If you can't see it, it might be an issue with your internet browser. So if you have another one installed, you can try to log into that instead. But at the end of the webinar, there will be a contact information for us anyway. So there will be a way to get in contact with us. Additionally, we prepared for you a short poll, which you should right now see on your screen. And we would really appreciate your short interaction and feedback with us. But no further delays, Veronica. Please continue with the presentation.
I think everyone is already looking forward to the application examples.
That's true.
So let's jump directly here. So in today's webinar, I'd like to discuss with you our use case on in-situ delayering and electrical characterization, and the second of them will be touching site-specific dopant concentration mapping. So for the first one, the task here is to how we can identify a connection failure or characterize it when it's buried somewhere within the structure in the depth. So how we can get here and measure the local conductivity, as the traditional techniques are quite complex and the analysis is quite time consuming. And so this is applicable actually to several structures such as 3D NANDs, logic, SRAM structure, vias or contacts, intercontacts, NVTs. And so we will show it today on the 3D NAND. As you know, most of the semiconductor structures are quite confidential. So this is where we can show it. So what you see is the polysilicon channel, which is a conductive one, and a silicon oxide core, non-conductive. And our solution for analyzing such structures is using AFM-in-SEM for the depth profiling by, as you've seen, partially the workflow from the delayering process to the navigation of tip, analyzing the conductivity and correlating it together. We can analyze larger areas or focus on on one via very site-specific place. And we can do this in the cycle several times. But some of you might not understand or know exactly what the delayering is. So the concept is quite easy. So there are several different polishing methods, millers, dimplers, broad ion beam. We used plasma FIB to delayer larger area. It can be in thicknesses over 400 nanometers. It can be much smaller as well, within single nanometers. The important thing is that at the end of the delayering, layer by layer, the layers are quite flat. So then it's suitable for the conductive analysis. So this way we can use the plasma FIB delayering. As you can see, we are under a large tilt with the sample, which is the highest point. Then we can either stay in the tilted position or get back to the standard version and analyze the conductivity. And this is what we can repeat over and over again. So for the conductivity mapping, we use contact mode. We bias either the tip or the sample. And basically, as we touch the surface at each point, we measure the current going through in between the probe and the sample. So that's why it's very crucial to understand where we set up the electrical connection, because otherwise it can change the experimental design very much. So this is the way how we can do the high resolution topography and conductivity mapping. And what you will see in the next experiment, we will be doing sequential delayering, allowing to access to layer by layer. This is the place which we've chosen, how it looks like after delayering or one layer fibbing, followed by finding the area of our interest and then analyzing with AFM and SEM. So this procedure is compatible with navigation file, so it's quite easy to precisely find the location of interest. So let's have a look at the non-structure analysis. So first of all, we analyzed layer 1 basically with no FIB milling. So this is the non-structure as it is with the surface oxide on top. So there's no surprise that we don't see any conductivity at this point. So what we did further, we analyzed, we sputtered a thin layer of tungsten, and then FIB milled a structure which is slightly more than the sputtered thin layer. And so what we see actually in the conductivity is intermixing between the conductive layer and the non-structure. So let's continue further. We did another layer. We uncovered and analyzed the structure. So we already can see that some parts of polysilicon channel are well visible. And when we continue further, we can nicely see the whole channel. And as it's polysilicon, the conductivity varies at the channel. We can as well analyze correlatively and put together the SEM view, AFM topography, and the conductive AFM current. This is the way how we can check for failures, either in SEM connected with the conductive AFM current, or we can check the quality of delayering, if it's smooth enough or something, for instance, weird is happening and some curtains are there and so on. So we can correlate large scales and find out specific area of interest, we can choose, let's say, this blue square and get closer to the vias. And we can as well get to a single via, so we can analyze a detailed view of the channel. We can see that the bright circle is the polysilicon conductive channel with thickness 10 to 20 nanometers, where the inner part is non-conductive silicon oxide core. How we analyzed it, we used a probe from nanocontact with a very high resolution FIB tip. So the diameter is around 10 nanometers. So this is how we can analyze very tiny structures. We can choose the IV spectroscopy points and analyze the current voltage characteristics. And further, we can, all of the data, we can correlate it together. So we can see an SEM tilted view under 45 degrees with high resolution tip above the sample and conductive AFM current map. To summarize this particular example, we've seen how we can analyze and use this the AFM-in-SEM or in FIB-SEM technology to analyze 3D non-structure, to do the plasma FIB delayering first, and then afterwards conductivity mapping at each layer within one vacuum cycle. So this enables us layer by layer conductivity maps. It enables us to detect resistive vias and defects in 10 or 20 nanometer channels. And simply it's faster, more precise, without the risk of contamination or oxidation. This example, this solution is applicable as well to smaller structures such as SRAM, logic, vias, and so on. So let's get to the MOSFET failure analysis. Here we're gonna work on the site-specific dopant concentration mapping. So the task here was to identify the dopant concentration and characterize the shapes and intensities of implanted dopants. Materials can be silicon, silicon carbide, gallium nitride, and more. And especially the interest is in the heavily doped layers below and between the gates of the transistor. This application is very useful mainly for the cross-section films or cross-section samples such as MOSFET, FinFET, CMOS, doped epitaxial layers. So as well, some level of sample preparation is needed. And our solution with AFM-in-SEM allows us directly analyze the dopant concentration using in-situ scanning spreading resistance microscopy technique. Also, we can calibrate it via reference samples for the quantitative information. We will show the measurement on the MOSFET transistor. So the architecture is a polysilicon gate in the isolation, and below it are different levels of implants and different types of the implants. In this, we will see a silicon carbide transistor. So then there are different layers below it. And as we can see here, we can analyze the cross-section, we can analyze a lamella. So it's very easy with this in-situ combination. Scanning spreading resistance microscopy, what this technique is. So basically, technique-wise, the analysis is similar to the conductive AFM. You also need to connect well the sample in order to have the good understanding what we are analyzing. And we analyze in contact mode. And depending when we push with the probe, we are generating a spreading resistance, which we analyze. And the spreading resistance can be then recalculated to the dopant concentration. And so how the in-situ workflow looks like. So I'd like to show you a recording. And as we created such a recording for the ISTFA last year, and where we won the contest, this recording was done by my colleague Radek, and he was actually inspired by swinging and jazzing of 20s. So enjoy, and you will see how we analyze. So first we'll lower the working distance and navigate the tip approach to the sample and measure. Then we rotate the sample for FIB milling. And analyze the lamella again. So I hope you had fun. So what we've seen lamella preparation with the analysis before on the chunk and on a thin lamella. So what we can see in the SEM are the different levels of concentration. So some of them we see well, and this we analyzed with the conductive, with the SSRM. We can see the current map of different stripes, different dopant concentration here. So the workflow is very similar to what you've seen for the first application example, but there is a difference in the calibration. So it adds 3 more steps. Doing the reference measurement, then we create calibration curves from the reference, we calibrate the measurement, and we can calculate the dopant concentration. And let's have a look at the first MOSFET transistor. We see oxide, non-conductive, gate, and then different levels and different types of implants. So we've chosen this area, and as we can see from the color, we see different shapes of N+, P-body, and epi layers. So we can see the shape, precisely find exactly the spot we'd like to analyze, and we see the intensities. So one part, then we analyze directly below the transistor to see the shape of different parts of N, N and P. And we can do several transistors. We can see if it's repeatable or not. And as well, depending on different connection with the sample, we can analyze different parts of the implants. We can as well play with the contrast. So as we can see, we can find out the best possible way to see the implants and see the shapes. We can also do the profiles, so you can see the resistance profile of the and analyze the size of the oxide layer between the gate and the N+ region. For the calibration, we are using different calibration standards. For the silicon, we use Infineon dopant calibration sample. And this sample has actually N-type and P-type stripes of different concentrations. So when we analyze such sample with our probe, we get the curve, we get the understanding between the dopant concentration, which is known for the sample, and calibrate our resistance data on the sample. If it's a different material, different substrate, and a differently doped epitaxial layers, we can as well do the cross-section. So when the sample is cleaved, we can get exactly to the region of interest on the border. So we see the probe holder, probe tip. From this side is the region of interest and a cross-section sample. So the benefit of such a solution is we can in situ analyze and we don't need to use external lab tools like SIMS or SRP. So we can directly put the AFM inside the SEM chamber and measure. We can understand the real sample context. We can visualize the doped layers using SSRM technique and compare it, correlate it with the SEM. And this is ideal for advanced materials such as silicon carbide, gallium nitride, or for instance, stacked FinFETs, where conventional profiling struggles. It's quite a good tool for the understanding of thickness of doped layers as well. So when we have a look with tilt 55 degrees, we see the very end of the tip and exactly where we analyzed. So as we can see in the SEM, we don't see much of the contrast. When using the SSRM map, we can clearly distinguish different epitaxial layers, measure the thickness from the profiles, and compare it with the SIMS. And this way, this can stand for the calibration sample for more difficult structures such as MOSFET or FinFET. To summarize this application example, we've seen how we can use the in-situ SSRM technique to analyze the dopant concentration in transistors with high resolution and inside the SEM. The key benefits are that we can directly map the implanted dopant shapes, depth, gradients. We can quantitatively profile via a reference-based calibration. This is ideal for several structures. We've shown it on quite a large structure, but it can be much smaller as MOSFET, FinFETs, CMOS, or epitaxial layers, understanding the junctions, or device reliability studies. To summarize what we've seen in the webinar, so we introduced the AFM-in-SEM with LiteScope, a solution which can greatly help in site-specific failure analysis, as we can measure electrical properties in situ inside the SEM chamber. We can directly merge the sample preparation and the analysis, correlate it together, and thanks to that, we reduce the time and costs per the analysis. We've shown the analysis on the solution on two examples. One is a non-structure failure analysis where we used site-specific plasma FIB delayering and then analyzed conductivity in different levels, layer by layer, which is applicable in SRAM, logic, intercontacts. Further, we had a look at the MOSFET failure analysis where we have seen the dopant concentration of individual transistor using in-situ SSRM, where we can test shapes, sizes, intensities, repeatability along the sample, and so of different implants and different types of implants. And we've seen it on this is applicable to FinFET, CMOS, SMOS, and so on. If you have any question, please get in touch. We will be happy to help you, or if you have any suggestion, discussion topic, we will be very happy to help out. In the meantime, Marek, where we can find more information or where they can meet us?
Thank you, Richard. Yeah, so the easiest way to get more information about us, our LiteScope, and its application would be definitely through our website, where you can download all the materials such as brochures or application notes. And you can also follow us on LinkedIn, of course, or watch some of the content on our YouTube channel. On top of that, you can meet us on site as well at some of these events. So if you are planning to visit any of these, get in contact with us and we would be happy to talk to you more at our booth. And finally, you can always contact us directly. So feel free to scan these QR codes and get in contact either with me or Alex. We would be happy to organize an on-site or online demonstration for you and to discuss your exact needs and application. Right, and I think it's now time for the Q&A session, Veronica, and there are actually plenty of questions there. I would like to start with this one from Jin. He's a bit worried and is asking how well the electrical characterization works for gallium focus ion beam, where the ion-induced layer removal will left a lot of gallium atoms inside of the sample. Could you please answer that?
Yeah. Thank you. So it's actually quite a good question. So you are right. Gallium can implant inside the structures. So that's why we rather use argon or xenon, which is a better inert gas, which we use, and we don't implant any additional dopants inside the structure.
Great, thank you. Second question I would like to pick. We still have plenty of time, so it should be fine to go through all of these. That one is from Dennis. So are you using self-sensing probes, he's asking? No optical detection.
Yes, you're exactly right. So we are using piezoelectric or piezoresistive probes. And for these analyses, we used piezoresistive. So from the voltage characteristics, we read the conductivity or the dopant concentration. So no laser is used.
Then we have one question from York, and he's asking if the AFM module is retrofittable or could be placed into an SEM. If so, what requirements are there for the SEM for it to work?
Okay, great question. Yes, we prepared and developed our AFM module to fit into existing SEMs, and you can as well choose and move it back and forth in your facility. So what is needed, basically the size of the chamber, we physically have to fit in, and the second thing, available flange, where we can take our cables out. Usually one is required.
Thank you. Then we can go directly to one of the newer one from Jaita. What is the resolution of the AFM? What is the maximum scan area?
Mm-hmm. So our resolution depends a lot on the AFM tips. So the AFM tips, for instance, for conductivity FIB ones, have the diameter 10 nanometers. So around that is our resolution for XY. For the Z direction, our resolution is 40 picometers. So in Z direction, we are much lower, as the tip does not interfere with that. For the maximum scan area, our scanner size is 100 micrometers. So anything around it is this is maximum scan area.
Thank you. Then we have another question here from Dennis. So, can you do scanning capacitance microscopy? This would give contrast without the delayering process. I might take this myself. Yeah, so this is a really on-point question, Dennis, and it's so on point that it's actually already discussed within our R&D, and it should be hopefully available with our next generation of LiteScope. So stay tuned and get in contact with us if the scanning capacitance microscopy is something that you would like to talk about and have. All right, then here a question from Leonard. How many samples can you mount at the same time for a comparative analysis?
Very good question as well. So for the standard scanner, we can load 3 samples. For the rotational scanner, basically there's 4 by 4 centimeters, as many as of the samples that you fit. It a lot depends on the size of your samples.
All right, yeah. And I have here a question which I forgot. Oh, sorry. One from Wojciech. Hello all. What is the current lifespan of your probe for conductive AFM and SSRM in terms of area and number of scan cycles, ideally?
Thank you for your question. So again, depends a lot on the sample and tip used. So for the conductive AFM that we've done on these applications I showed in the webinar, there can be dozen of samples or dozen of scans. Our scans, I believe we did up to 20 micrometer range.
Great. Yeah. We have more and more questions coming in. That's great, guys. Thank you. We have a question from Ladislav. Are you limited with the maximum depth during the PFIB delayering? So, the cantilever could still fit in.
Yes, you're correct. And here I actually don't know the exact number. As the probe height is probe tip height, I don't know, it was within several micrometers. So
I think, Veronica, you have a help of Radek right there.
But I didn't find the question, so I didn't find the answer.
Oh,
so
sorry.
this I don't know from my head, but basically you can as well FIB mill the structure so the cantilever can go even lower. So usually about 15 microns. Yeah, I found it out. Sorry for that.
No worries.
So there is plenty of layers actually you can analyze.
Then we have a question coming again from Jaitza. So is PFM, so Piezo Force Microscopy, also available on the AFM?
Yes, it is available. You can use it.
That was an easy one, right?
Yes.
And okay, I need to refresh this. There is a question from Javier. Are there any specific settings or setup for the MFM analysis other than the tips?
You're correct that the tips are the most important part that we need to have the magnetic wire on top at the end. And we are using a 2-pass technique. So basically different from the conductive AFM is that we're not going once and then on another line, but we're going twice per line.
Thank you. Thank you very much. If I am correct, let me just double check this. I think we've reached our last question for today. So once again, thank you very much for all of these questions and for your interaction. And I believe with this we can actually close today's session. So I would like to thank my colleague Veronica again for the beautiful presentation, all of you for your attendance, for coming. And if you want to get in contact with us and discuss your exact needs and application and how it can relate to our LiteScope, please scan these QR codes and we would be happy to get in contact with you and discuss it. Thank you very much and enjoy your day.
Thank you very much for coming. Have a nice day.